Well, it's time to look at climate change itself. How about that? Are you tired of hearing about it? Well, sometimes I get tired of talking about climate change. I've been talking about it more or less for about 20 years, and then some before that. A lot has changed over the years. The evidence is way stronger that it's happening and that humans are causing it. Um, about what the public feels about it because of the way the power groups operate, um, and our perception through the media is variable depending on what time frame you're in. That's not something I'm going to cover in this particular unit, though, but I'm going to address it in a way, and you'll kind of get a sense of that. So, and the way that I approach it. So let's have a look. Basic question. This is the single most basic question, I suppose, we could do about climate change. Now, there's more things than just temperature, of course, and later we're going to look at a lot of what climate change isn't really about temperature as much, or it's about temperature, but it's affecting something else, which becomes really the problem. So, nonetheless, this is the key important question. So, is it getting warmer? What do you think? So, there are a number of, well, there's literally thousands of weather observers around the country in the United States. Just that isn't the whole climate of the world, of course. And the single most significant former career for those people, most of them are men, and most of them, largest group is retired military as weather observers. So they're a pretty, fairly conservative group of guys overall that are doing most of the observations. And then the data gets compiled by national and then international agencies. And so Japan has its own climate data service. So does the UK. It's called the Hadley Center. And then we have NASA in the United States, and also NOAA, National Oceanic and Atmospheric Administration. So let's look what we have here. The answer is yes. Okay, so class dismissed. Let's go do something else. Bye. Well, no. um, but look at this, just the second line on this. 2015, 16, 17, 18, and 19 are the 5 warmest since thermometer measurements began in the 1950s. I kid you not. So, in looking at this, there we go. Click that a little harder. This is a great site. It shows a lot of things, but one of them that's of note here is the temperature record. And where you go here is you just click on the global average temperature and you have a look at the bars. I'm going to zoom in on that a little bit. I got to remember to get the Control Plus out later. Could you remind me to take that off later? Okay, just joking. So look at this. 1880s. All these years, average global temperature. All this is, by the way, the long-term average from 1900 to 1980 is this flat line here. Okay. So what's interesting to me about this is that once we hit about 1980, has not been a single year since that was the average temperature over this time period. Wow. Um, the very warmest one wasn't 2019, it was several years earlier, 2016, I guess that was. But that's what I call a statistically significant trend. All right, so let's go back. I'll zoom back out, and we will go back up to the other notes here again. Now, imagine that you were someone who is still skeptical. I've heard conspiracy theories like, they're fudging the records as if somehow you could unite weather observers and national agencies all over the world to show bias upward. But, that being what it is, What else would we look at? Let's say we couldn't trust the temperature record. And by the way, we can. But let's just for a moment, just for sake of argument, say we couldn't. What else would we look for? And if you think about this a little bit, this is kind of like maybe middle school level stuff in terms of what happens, the processes, right? So, gee, what happens to ice when it gets warmer? The rate of melting of ice. What happens to it when it gets warmer? It melts faster. What happens if you have warmer air over oceans? What would happen to ocean temperatures? They would get warmer. If you were melting ice in glaciers and it runs into the sea, which is what happens, so it goes around the sea, how would we know that that was happening besides observing it? How would we know that there was more water running into the sea? Sea level would rise. So these are all the kind of things that you can, it isn't, you don't have to have a degree in physics to understand at this level. This is really kind of common sense. Here we are. So that should be a 2, by the way. I don't know why I can't get rid of that. I think when I put this space in here, sorry about that. Anyway, that should be number 2. Just notice that. Globally representative mountain glaciers with the longest, most reliable records lost 72 feet of thickness from 1980 to 2016, and 57 feet by 2014. In other words, from 2014 to 2017, they lost another, 15 feet in a very short amount of time. They've been accelerating. The global average sea level rise that we mentioned has accelerated. And it is accelerating rapidly. It used to be that thermal expansion and melting were roughly contributing the same amount to global sea level rise. Let me explain that. Thermal expansion, so warmer water does expand a little bit, not a lot, but when you have a whole ocean basin, it's, a few miles deep. In some places, a little thermal expansion goes a long ways from the melting and then the running off the water, right? And nowadays, though, the melting has taken over, and it's almost 2/3 of all of the total global sea level rise is now melting. So that's a new thing in the last 10 to 15 years. They used to be roughly contributing the same amount. Subsurface ocean temperatures. Okay, so it's not just sea level rise, but we can look at the below the surface of the ocean, the upper 75 meters, which is about 250 feet almost, have warmed 0.09 to 0.13 per decade since 1971, when the most thorough measurements began. I had a student actually taking this class from me maybe 5 or 6 years ago now. He worked in the Navy on ships, and he was involved in actually doing those measurements. It was so fun because I remember giving this lecture, and his guy's eyes got all wide, and he basically just raised his hand, and I called on him. Really bright guy, maybe 40 years old. And he described how they did it. And it was so cool because all the class got to hear about it. So not only the service, but think about that, all that energy required to warm up water. It's a huge amount. Remember the specific heat of water? So to warm it up that deeply is really an incredible thing. So those are 3 additional pieces of evidence beyond the original, hey, it's actually getting Rome warmer based on thermometers. So these 4 are kind of the big ones that I usually use. There's a lot of other evidence too. One is that they've been boring deep holes in various parts of the world and measuring temperatures down. I think it's 100 feet deep they do, and there's a detectable temperature rise even 100 feet deep. Think of that. So there's a lot of things like that that are being measured as well. But these are just the kind of the key ones. The other one I could have put on here is not just mountain glaciers like we have in this middle one here or this one right up here, but also the continental ice sheets of Antarctica and Greenland, and they're also melting. So that's different from mountain glaciers, and that's the other one I can put on here. In fact, that has great potential for large sea level rise. Something you've already seen, the huge amount of mass in the glaciers from the hydrologic cycle stuff we did earlier. All right, so now the big question. Have human activities caused global warming? So again, yes. Okay, but let's be a little more careful and systematic, right? So to really answer that question with authority, though, the kind of authority you expect from me rather than some television personality, is to look a little bit at how we come up with answering that in a reasonable way. The first thing is if we're going to show human causation, we have to require both demonstrating one, that human emissions can account for the observed warming trends, and number two, showing that other potential explanations cannot. Right. So I mean, if ours could do it, what we've been doing could account for it. If we look at the basic physics, what we understand about the science, we say, okay, so what we've done could do with all those extra greenhouse gas emissions. But you still say, well, but couldn't it be something else? So even if what we've done would be sufficient, if there was some other potential explanation out there that also could have done it, and we've seen that, in fact, where it would be in operation, then we have to look at that to be intellectually honest with ourselves. So we have to start with the past Earth climate has shown significant temperature variability long before human societies were capable of causing it. Wow. Yeah. I mean, we have a huge, huge, huge record going back before we were even here. Okay. And so, in doing science, there's the kind of model of observation, explanation, and prediction. And we can be time travelers. And we're going to learn a bit about that. And you may have already watched the Richard Alley ice core oxygen bubble, carbon dioxide bubble story. And if such, then you kind of know what that's about. But in any case, um, what we need to do then, if we're going back, if we're going to look at other potential explanations, that we have to look at that natural variability in the absence of significant human influence carefully. So let's look at the leading possibilities here. Natural causes of temperature variability. First one is Earth-Sun orbital variations. The Earth-Sun distance varies over 100,000 year cycle. The average distance does. Related to that, Earth-Sun relations is the seasonal timing of when we get closest to the sun. The perihelion varies in a 26,000 year cycle. We're currently in the cold phase for our hemisphere, when for us, the July 4th is actually when we're farthest from the sun, and we're in the warm phase, January 3rd. Okay. And that varies, and so it actually reverses gradually. But here we are. And if anything, that's favoring, since we're actually in our cold phase during the summer, not melting ice in the Arctic, which is a driver of climate change. So in this sense, we ought to be getting a little colder because of that particular one. The axial tilt varies from about 22 to almost 25. It's about 24.5. I kind of rounded there. Over a 40,000 year cycle. And think about this, when it's tilted more toward the sun in the summer, think about that. Our summers, when it's tilted toward the sun, that's what makes it warmer in the summer. The more it's tilted towards the sun, the sharper the tilt, the more it is able to melt ice of the glaciers. So that favors a deglaciation. Since we're in a decreasing phase, 23.44, and getting smaller, that number is getting smaller, we are on our way to cooling if it were just these two factors here. Okay. There is strong scientific consensus that these cycles are associated with the cycling between ice ages and warm interglacial periods over the past few 100,000 years. These changes are slow and are thus unlikely to have caused the rapid warming of the last 100 years. The second factor is tectonic activity. It affects the latitudinal locations of the continents and geochemical processes that can affect total snow cover and atmospheric chemistry. These changes are also too slow. They happen very, very slowly over the last millions of years. Not going to be the explanation. We're talking about changes that have happened very fast.